Roman numeral 3 plus the preceding page, page 11 of your handout, dealing with specific heat capacity, because that goes much better with Roman numeral 3, which will start on the next page. So specific heat capacity, it is defined as the amount of heat energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. It has the symbol C sub S, and it has units of joules per gram degree Celsius. Joules per gram degree Celsius, which can also be written joules on the top, grams in degrees Celsius on the bottom. We'll see some equations coming up in a couple slides with this term in it. I did want to make a point that we will see that in this particular case for specific heat capacity, units of joules per gram degree Celsius or joules per gram Kelvin are equivalent. We will see that because it's a change in temperature, so to raise or lower, but the definition includes the word raise. So to change the temperature a set amount of degrees. So when you think of temperature changes in degrees Celsius and Kelvin, they will be equivalent. So, and you could see either of these sets of units. Let me show you what I mean by that. So if we think of the boiling of water, and we think of the temperature at which that occurs for in degrees Celsius, we would say 100. In Kelvin, that would be 373 Kelvin. Now let's think about the freezing of water. In degrees Celsius, that occurs at 0 degrees, which is 273 Kelvin. Now, if we look at the temperature change in each of these cases, we can see that numerically they are the same, and that's because a degree Celsius and a Kelvin are the same size. The only difference is they're offset by the number 273 from each other. So the take-home message is that when we do specific heat capacity, it will involve changes in temperature. Changes in temperature in degrees Celsius or Kelvin are numerically the same, and so you will see each or both of these sets of units as we work problems. All right. Now, Roman numeral 3, where we introduce what's called delta H reaction. It is the change in enthalpy of reaction, and functionally, or a working definition, is it is a measure of the heat energy gained or lost for a reaction at constant pressure. And an exothermic reaction or system, to use the phrase that we've started to use, has delta H less than 0. I put just delta H there because we'll see a couple different subscripts there as we go through this chapter, for which all, when they are less than 0, the reaction is exothermic. And an exothermic reaction has the reaction releasing energy to the surroundings. As an example, I have the combustion reaction here for propane. We've seen this one before. We can even be asked to write combustion reactions. This one comes balanced. We see that the products are carbon dioxide and H2O gas. And this is in a type of information that you'll see in problem statements that you'll be solving on the homework, where delta H reaction is given minus 2044 kilojoules per mole. So the minus sign means that this is an exothermic reaction, and our way of thinking about that is this is the amount of energy per mole that is produced. So that's what it means when it's releasing energy. So 2044 kilojoules per mole are produced by this reaction. And one helpful thing to do that I like to do is if it's a product, write the energy as a product. And I've put in plus here even though there's a minus sign here, or minus 2044 kilojoules per mole produced. The minus sign tells you it's produced. So this is a little redundant, but better to say the same thing twice than not at all. Minus 2044 kilojoules means it's produced. It says produced right there. And it's a product. And another note, there will never be anything negative in this reaction. So this plus here means it is produced. Okay, so exothermic reaction has delta H less than 0. It's a negative number. It is releasing energy. And what we can do is we can write unit conversion factors for this. And I'll write a couple of them. So I like to treat this 2044 as the coefficient. And so let me show you what I mean. So I'll put back in the minus sign and say there are minus 2044 kilojoules, or that much energy produced, per 1 mole of propane. Okay. And that's where the per mole comes from. It comes from if there is a 1 coefficient. Now, where it's complicated a little bit more anyway, is that this same amount of energy is produced. And again, after right now, we won't write the produced part. Per 5 moles of oxygen reacted. There's a unit conversion factor. And I know, so it says per mole, but that's per mole of thing with a 1 coefficient. It's per 5 moles of O2. It is per 3 moles of carbon dioxide. And we could do something similar for the H2O. All right. So that's for an exothermic reaction in which energy is released or produced. We are going to now look at what's called an endothermic reaction. That has delta H greater than 0, and the reaction taking in energy from the surroundings. And we'll always be looking at this from the system or the reaction's point of view. And so when the reaction takes in energy from the surroundings, that will be considered positive. Now, what I like to do here, what you'll notice is that I've flipped the reactants and products. That has changed the sign of delta H, but not the number. Let me say a few words about that. So we said that as you do a reaction, you are going to change the positions of the atoms. Those positions are going to change the potential energy. And so we're going to say that delta H is an indication of the change in potential energy of the atoms as they go from reactants to products. And as that happens, this release or taking in of energy, this is a taking in of energy, from the surroundings is going to be energy that is incorporated or released from this reaction. So let me see if I can say that slightly better. So as the positions of the atoms changes, there will be a change in potential energy. That change in potential energy is associated with bringing in heat energy from the surroundings. Heat energy is from kinetic energy of the surroundings. So we have potential energy of the atoms in the reaction. We have heat energy, either in this case coming in from the surroundings to change that potential energy. Anyway, we'll say more about that. For now, I want to show you that this is greater than 0. Energy is taken in. That is endothermic reactions. And we can put plus 2044 kilojoules as a reactant. So energy is a reactant, or energy can be thought of. Energy is a reactant going into this reaction to make the products. Okay. All right, so delta H is the change in enthalpy of reaction. The rest of the chapter is how do we measure and use delta H reaction, what does it mean, because it's going to be an amount of heat energy, we're going to say things that relate it to the number, or to the potential energy of the reactants and products. All right, but we need a system for measuring it, for calculating it, and here's our first one. We use a coffee cup calorimeter. A coffee cup calorimeter is literally 2 coffee cups. Styrofoam is best because they are the most insulating. Put an insulated cover on top, a thermometer, a stir bar. You can also swirl so that you don't need the stir bar. And then we have some solution in here, or some water, as we'll see. All right, so we will see that when we place reactants inside cups, that the system will typically be 75% plus reaction, 25% material. And I'll show you again what this means more specifically. Again, that is the definition of the system. The surroundings is everything else. Including the water or solution. And the assumption when using a coffee cup calorimeter is that the coffee cups are perfectly insulating. Which means no heat escapes or goes into the coffee cups. No heat goes into coffee cups. And therefore, all of the heat from the system, whether it's a reaction or material, all heat from system goes to surroundings. And I'll show you on the next page, we have an equation that does that. Q, lowercase q, is our symbol for heat. So Q for the system equals minus Q surroundings. And the minus sign only shows up because there's a change in the direction of heat flow. If the system is giving off heat, then the surroundings is taking heat in. There's a directional difference there, and that's what the minus sign means. The Q system could be positive or negative, doesn't matter, it depends on if the reaction, if it's a reaction is endothermic or exothermic. All it says is if this gives off energy, this takes it in. If the reaction system takes in energy, then the surroundings are giving off energy. All right, so now we have the coffee cup calorimeter equations. I'm going to ask you to draw a line down the middle. We do have 2 cases. We have that the system is a reaction. And we have the system as a material. So similar, though, I think it's best to keep these two sets of equations separate in your mind. I don't know, we'll see as we go. System as a reaction, then Q system becomes Q reaction. It is equal to minus Q of the surroundings. And what we will see is that the surroundings in the coffee cup calorimeter will be everything, but since the coffee cups keep all of the heat energy inside, then functionally the surroundings are the solution inside the coffee cups. Now I'm going to keep working these. So the solution, and remember Q is heat. Q solution is going to be the mass of the solution times the specific heat capacity of the solution times the temperature change of the solution, where temperature change will always be the final temperature of the solution minus the initial temperature. And that goes for all changes. It's always final minus initial. Okay, now a couple things about the solution. So, and we'll see this in our examples. The solution will be an aqueous solution in which water is the solvent, and it will be 90+% water, which means we can make two assumptions. One is that the specific heat capacity of the solution is equal to the specific heat capacity of water. Which is 4.184 joules per gram degree Celsius. The other is that the mass of the solution, the density of the solution is the same as the density of water. And where the density of water is 1.00 gram per milliliter, which means that in a problem, if I say there are 250.0 milliliters of a certain solution, we can assume that that is 250 grams of solution. Okay? All right. So that's the setup. That's the solution part. Now let's do Q reaction. Q reaction is going to be the one that's quite different. It is going to involve our delta H of reaction, since there is a reaction in this problem. And that's going to be times moles reacted. And it won't come up very much, but these are moles reacted with a 1 coefficient. We saw that coefficients matter in the relationship to delta H. If it comes up for us, I'll let you know. All right, so, and the way that you solve problems is there are 1, 2, 3, 4, 5, 6 different things that you need to know. And of course, in typical Chem 1010 fashion, we'll give you the information for 5 of them, and you'll have to solve for the last one. The last one mostly being delta H reaction that you'll have to find. Anyway, we'll do some problems coming up, but this is the overall setup. It's similar when the system is a material. Let's assume that the material is aluminum, and that aluminum is being placed in, will typically be placed in water. So aluminum, so placed in water. The material is typically placed in water. You'll see a couple times where there's 2 different materials, but typically it's a solid placed in a liquid at least. This time it's the heat of the aluminum equals minus Q or the heat of the water. So this just says all the heat given off or taken in by the aluminum goes to the water or comes from the water. Now these are two materials. These materials, so no reaction involved. They will both have identical terms to this solution part over here, meaning that Q aluminum equals the mass of the aluminum times the specific heat capacity of the aluminum times the temperature change of the aluminum. Same thing for water, mass of water times the specific heat capacity of the water times the temperature change of the water. And I think the one thing that comes up pretty frequently in these types of problems is that we're solving for T final, and that in these types of problems, T final is the same for the aluminum and the water because you'll be mixing them together. So T final is the same for aluminum and water. You won't in fact have two separate T finals. They'll both be the same, and that's what you'll be solving for, as I think we'll see. That seems like a good place to stop. We'll save the examples